Okay. So all right. A very good evening all. In the morning session, we discussed regarding the three-phase half wave uncontrolled rectifier. Yes. Now we are going to discuss the three-phase full wave uncontrolled rectifier with the RL load. In the morning session, we already discussed the R load, right? For uncontrolled rectifier, RL load, R load, the operation will be same. Here the negative pulse will not appear, right? We'll discuss how. After that, we'll be discussing about the three-phase full wave controlled rectifier for R load and RL load. Next, we'll be discussing about the Fourier series analysis in order to get the input power factor expression. And after that, this three-phase semi-converter, right? Okay. So let me put the heading: three-phase half wave uncontrolled rectifier. Three-phase full wave uncontrolled rectifier with the RL load. Okay. RL load, right? So recall the circuit diagram. We're having a 6 diodes connected in a bridge configuration. Okay. Load is RL load. And here we are having a three-phase input supply. It is a balanced three-phase input supply. Supply terminals are A, B, and C. We considered this voltage as VA. Here it is a VB, and here it is a VC, right? Diodes are D1, D3, D5, and D4, D6, and D2. The load is RL. This voltage is V0, and current is a I0, right? So, as we discussed in the morning session, at a time, two diodes will be in a conduction mode. One from the upper group, second one is from the lower group. Okay. So, if at a time two diodes will be in a conduction mode, then definitely the current will be flowing like, suppose D1 and D2 are in a conduction mode. So current will flow like VA, D1, load, D2, and again back to the VC. So the voltage across load is equal to VA minus VC. That is a VAC. So VAC is the line voltage or phase voltage. It is a line voltage. Yes or no? Right? Similarly, you can consider suppose D1 and D6 are in a conduction mode. So the current will flow from VA, D1, load, D6, and back to the VB. So V0 is again equal to VA minus VB. That is the VAB. Okay. So VAB is also line voltage. So here, when at a time two diodes will be in a conduction mode, one from the upper group, second one is from the lower group, then the voltage that we will be getting across the load is nothing but some portion of the respective line voltage. So here we are having the supply voltage is nothing but the line voltage waveform. Okay. So here we are having a supply voltage waveform which is equal to the line voltage, right? It is nothing but a line voltage. This is your VS. Okay. This is angle omega t. Let me write it as omega t, right? So here we are having the line voltages. So you can check here in the morning session also we discussed we are having the phase voltages as VA, VB, VC. So the line voltages will be like VAB, VBC, VCA. Just like a VAB will be having VBA, just like a VBC will be having VCB, and just like VCA will be having VAC. So these 6 line voltages we are having, right? So that's why we are having the 6 line voltage waveform. So here we are having the 6 line voltages. Yes, you can check solid black and dotted black, right? Solid yellow and dotted yellow, solid green and dotted green. So like this we are having the 6 line voltages. So line voltages, let me write it as this. Suppose this is a VAB, this is a VBC, and here it is a VCA, right? Now you can check, I have written this as a VAB. So let me write VAB expression first. VAB is a line voltage at omega t is equal to 0, it is a 0, right? At omega t is equal to pi by 2, at omega t is equal to pi by 2, it is at its peak value, na? Omega t is equal to pi, it is again 0. Omega t is equal to 270 degree, it is at negative peak value. Omega t is equal to 2 pi, it is a 0. Okay, so this indicates your 2 pi radian. This is like a 2 pi radian. Okay, so let me write here, can we write VAB is equal to VML into sine of omega t. You can check, when omega t 0, VAB 0. Omega t pi by 2, VAB peak value. Omega t pi, sine of pi, VAB will be 0, right? Like this. Similarly, we can write VBC. You can check VBC. Here, each interval is of 30 degree. Okay, interval in the sense, yes, you can check here. This is 0. This is like your pi by 6, that is a 30 degree. This one is like pi by 3. This is like a pi by 2. Okay, here it is a, let me write it as, yes, pi by 6, 2 pi by 6, 3 pi by 6. Okay, so it is a 4 pi by 6, right? 4 pi by 6 means 2 pi by 3. Next, this is like a 5 pi by 6. And here it is a 6 pi by 6 means pi radian. Okay, after 6 pi by 6, here it is a 7 pi by 6. We are having a 7 pi by 6. Next, 8 pi by 6. 8 pi by 6 is like a 4 pi by 3. Next, this one is a 9 pi by 6. Okay, 9 pi by 6. 10 pi by 6, right? Here it is a 10 pi by 6. Similarly, you can check 11 pi by 6, and here it is a 12 pi by 6 means 2 pi. Okay, so each interval we are having, it is a 30 degree. So VBC is lagging to VAB by how much angle? It is a 2 pi by 3, na? Right? So can we write it as VML into sine of omega t minus 2 pi by 3. Similarly, you can write VCA also, which is equal to VML into sine of omega t minus, you can check VCA is lagging to VAB by 4 pi by 3, na? So minus 4 pi by 3. Either you can write it as minus 4 pi by 3 or plus 2 pi by 3. Both are the same, right? Now you can check VAB is a solid black. You can check now dotted black here. The dotted black is exactly phase opposition to that of the VAB, na? This is a positive, dotted black is negative. So it is a completely out of phase. So can I say that if this is VAB, solid black is a VAB, so can we say that this dotted black is nothing but VBA, right? So this is a VBA. Let me write here VBA. Similarly, we are having VBC, opposite to that of the VBC, that is a dotted green. Okay, so opposite to that of the VBC, that is a VCB, right? And similarly, here we are having VCA, and opposite to that of the VCA, that is the dotted yellow, it is a VAC. Okay, so we are having a 6 line voltages. We are having a 6 line voltages. Next, now in the rectifier circuit, if you check, this is the uncontrolled rectifier. So at a time, as I said, 2 diodes will be in a conduction mode. One from upper group, second one is from the lower group. Which diodes, right, will be in a conduction mode, that will be determined by these respective line voltages. Okay, across which diode pair the maximum voltage is appearing, na, that respective diode pair will be in a conduction mode. That respective diode pair will be in a conduction mode. Now you can check here. Yes, this point is like pi by 3. This point is like a pi by 3, right? So here you can check from pi by 3 to 2 pi by 3. From pi by 3 to 2 pi by 3. VAB is maximum, na? VAB is a maximum. So if VAB is maximum, yes, if, let me write V0 also, omega t V0, and next one is the I0. Load is REL, I0 is the constant current, right? This is your constant current I0, right? Now here you can check VAB is maximum during pi by 3 to 2 pi by 3. So during pi by 3 to 2 pi by 3, VAB is maximum. VAB means VA minus VB. So definitely diode D1 and your diode D6 will be in a conduction mode. Please try to understand this. VAB is maximum means the current is flowing from VA, D1, load D6 and back to the VB. Okay. So here current is flowing from VA, D1, load D6 and back to the VB. So D1 and D6 will be in a conduction mode. Diode is uncontrolled switch, we know, right? So therefore D1 D6 conducts. So when D1 D6 conducts, V0 is equal to VAB will be getting. Okay, so it is like our inductor go on storing the energy till the instant our VAB will be greater than this VR. Okay, will be greater than the VR, and after that it will release the energy. Okay, it will release the energy. Next, so now here in the output voltage you will be getting the waveform. It is like a VAB only. From this instant to this instant, it is a VAB. This type of waveform will be getting in the output voltage. This is a VAB, right? So what is happening when T1 DC conducts, inductor stores energy, and after some time, after some angle, after some instant, it will release the energy again. It will release the energy, okay, through this D1 D6 only. Next, you can check here at 2 pi by 3, at 2 pi by 3, okay, at omega t is equal to 2 pi by 3, VAC is a peak, na? VAC is a maximum compared to the other 5 line voltages, okay? So if VAC is a maximum, VAC is maximum means current should flow from VA to the VC, okay? So therefore D1 and D2 will be in a conduction mode. D1 and D2 will be in a conduction mode, right? So when D1, D2 conducts, current will flow like this, VA, D1, load, D2, and again back to the VC. Once D2 turns on, what will happen to D6? Once D2 turns on, yes, this D6 will feel the reverse voltage and turn off. We'll discuss how it turn off, okay? So once D2 turns on, it is like when here it is VC voltage, definitely here voltage is VC, na? You can check this potential is equal to this potential. Again, this VC diode D2 is in a short circuit, so that's why it is a VC here. Same VC here, it is a VC we'll be getting. So at the anode of diode D6, voltage is VC. At the cathode of diode D6, the voltage is, this is VB, means definitely here it is VB, and here it is the VB, na? So you can check the voltage across diode D6 is VC minus VB, right? That is the anode voltage is VC, cathode voltage is VB. So what is the voltage? VC minus VB means VCB. So you can check once D2 turns on, okay, when D2 turns on, what is the voltage? VCB. What is the voltage? VCB. So you can check here the D2 is turning on at this instant, right? So corresponding to this instant, if you check VCB, okay, we are having a VCB. So this is VCB, dotted green, you can check. So at this instant or after, just after this instant, this point is nothing but this point, na? Just after this point, we are having VCB is negative. So VCB negative, what it indicates? Our diode D6 will feel the reverse voltage and diode D6 will turn off. D1, D2 will be in a conduction mode. Current will flow from VA, D1, load, D2, and again back to the VC. So in the output, we'll be getting VA minus VC. That is the VAC. That is the VAC, right? So during this interval, again, what will happen? Inductor stores energy, and after some time, it will release the energy. We know na, in a single phase, full wave rectifier we discussed. Actually, the inductor stores energy from omega t is equal to that. Suppose for diode rectifier, it is from omega t is equal to 0 till omega t is equal to theta, like thing we are having. Okay, and that theta is determined by, yes, your value of R and L. Okay, and VR, voltage across resistor, is VR. If VS is greater than VR, it is like your VL will be positive. Okay, if VS is equal to VR, VL will be 0. And after that, if VS is less than VR, VL will be negative. Okay, so the instant at which VS is less than VR, okay, during that interval, our inductor releases the energy. Okay, releases the energy, right? So now here in the output, we'll be getting now VA minus VC. So VA minus VC means output voltage will be VAC, right? Output voltage is a VAC. Let me write here. VAC will be getting. Okay, VAC. So this is the VAC, right? Next, here, this will continue till pi. After pi, yes, VBC is a peak value now. VBC is a peak value means what? Between VB and VC, okay, current should flow, means current should flow from VB to the VC. So it is like VB, D3, D2, and again back to the VC. Means what? Here diode D3 will turn on. Once D3 turns on, your diode D1 will turn off. You can check once D3 turns on how the reverse voltage will appear across diode D1. You can check here. This is VB, this is VB. Therefore, here it is VB. Definitely here it is VB. Right? Once D3 turns on, check the voltage VA minus VB, that is the VAB. You will be getting, it is a negative voltage only. Okay, so yes, so D3 and D2 conductors means output voltage will be VB minus VC, that is the VBC will be getting. Output voltage will be getting as a VBC. Right. So here we'll be getting VBC. This type of waveform will be getting. Right. So you can check after pi na VAB is negative. VAB negative means your diode D1 will turn off na, right? So which diode pair will be in a conduction mode? It is like D2, D3 now conduction mode, right? So now you can check. Yes, it is like AB was conduction mode means at that time when VAB was appearing at that time, the diodes D1 and D6 were in a conduction mode na. So here conduction is like D1, D6. Let me write here D1, D6. Here it is like a D1, D2. During this interval, it is like a D2, D3. So it is like sequence you can check D6, D1, D1, D2, D2, D3. Next will be definitely your D3, D4. Next will be D4, D5, right? And after that D5, D6. Okay, so here we will be having the D5, D6. And so that we have given the numbering like this, na 1, 3, 5, 4, 6, 2. This numbering should be like this only, then and only then this will be your value. This operation of the switches, okay, or the sequence of the switches will be valid, right? Otherwise it will not, right? So similarly you can check after this, just like we discussed in the resistive load, same is happening here. This is a VBA. Next we are having a VCA. VCA, and similarly we are getting at this side, this is a, yes, whatever the waveform we are having, the same waveform will be getting here. Yes, right, this is a VCB. So waveform is same for a R load as well as for RL load. Okay, it will not go into the negative. Why we are taking line voltages and not phase voltages? Because the thing we discussed in the morning session also, at a time two diodes will be in a conduction mode na, one from upper group, second one is from lower group. So you can check when one from upper group, second one is from lower group conducts, the voltage that will be appearing across the load is nothing but your line voltage na. Whereas if you recall in the three-phase half-wave rectifier, okay, in that case we had only three diodes. At a time only one diode was in a conduction mode, and when one diode was in a conduction mode, at that time the voltage across the load appearing was like your phase voltage. So that's why in a three-phase half-wave rectifier we consider the supply voltage is a phase voltage, whereas in this case supply voltage is nothing but your line voltage. Are you getting the point, right? So no, we cannot change. You can change the diode numbers, but please be sure that if you change the diode numbers na, here you will not get the sequence like this: D5, D6, D1, D6, D5, D6, D6, D1, D1, D2, D2, D3, D3, D4, D5, D6, right? This type of sequence you will not get. If you change here numbering like 1, 2, 3, 4, 5, 6, then this sequence will be your different, right? So generally in most of the books they have kept this sequence only, right? Next, so please keep it in mind, for uncontrolled rectifier, the waveforms for voltage waveforms, output voltage waveforms for R load as well as for RL load, both are same, okay? Because whatever the next pair of the diode will be in a conduction mode, right? Inductor can easily release the energy through that pair also, right? Because here the opposing voltage is not there, right? Next, but whereas if you recall in a three-phase half-wave controlled rectifier we discussed for RL load, unless and until we apply the gate signal to the thyristor T2, okay, inductor required to release the energy through thyristor T1 only, that too in opposition to that of the supply voltage, okay? But here it is not happening, right? It is not happening, okay? So whatever the expressions we derived, okay, for R load, same expressions will hold here, okay? Same expressions will hold here, okay? Let me write in short those expressions here. Yes, V0 average. Yes, we are having total 6 pulses na. corresponding to 0 to 2 pi, corresponding to 0 to 2 pi radian, we are having a 6 pulses. Okay, so it is like a 6 by 2 pi. Integration from, you can check VAB is present from during this interval from this point to this point. So this instant is like your pi by 3. This instant is like 2 pi by 3. No? Okay, so I am writing it as pi by 3 to 2 pi by 3. What is the VAB expression? It is a VML into sine of omega t. Okay, so it is a VML into sine of omega t into d omega t, right? Next, we can simplify it, and from this V0 average we can get. Okay, this expression is same as that of your R load expression. Okay, next V0 RMS is equal to 6 by 2 pi, integration from pi by 3 to 2 pi by 3, VML square into sine square of omega t into d omega t. Same expression we have already derived in the R load. Okay, purely resistive load in the morning session. Okay, so no need to derive here again. V0 average, V0 RMS. What is I0 average? You can check the I0 waveform. It is a constant, na? What is I0 average? It is a I0 only, na? Yes or no? Right? So I0 average is equal to I0, or you can write which is equal to V0 average by R also. V0 average by R also, right? Next, I0 RMS is equal to again capital I0. Okay, I0 RMS is again capital I0. Conduction time of each diode, conduction time of each diode pair, we already discussed that, and same will hold here also. Same will hold in this case also, right? So this is about your RL load. Okay, you can recall RL load in a case of 3-phase half wave as well as 3-phase full wave uncontrolled rectifier case. Okay, the waveforms are same, means same as that of your purely resistive load waveform, I am saying. Okay, next, now we are going to discuss the controlled rectifier, 3-phase full wave controlled rectifier. Okay, with a purely resistive load, right? Now we are going to replace the diodes with the thyristors. Okay, so 3-phase full wave controlled rectifier. You can write 3-phase full wave controlled rectifier or 3-phase 6 pulse also you can write, doesn't matter, both are same. Okay, let us consider the load is R load, resistive load. Okay, so circuit diagram similar to that of the previous case. The only thing is we need to replace the diodes with the thyristors. Balanced 3-phase input supply. Yes, let me write here VA, VB and VC. VA, VB, VC, these are the phase voltages. Okay, so thyristor numberings are 1, 3, 5, 4, 6, 2. This voltage is V0 and current is a I0. Okay, current is a I0. Consider this phase A current is a IA. Consider thyristor T1 current is IT1. Okay, IT1, right? So sometimes they have asked the question like what is the RMS value of the phase A current? Okay, generally we find the expression for the I0 RMS. Okay, but what is the RMS value of the phase A current? What is the RMS value of the thyristor current, each thyristor current? Okay, this type of questions also they have asked. Okay, we are going to derive those expressions also, right? So now, so here we are having a 3-phase full wave controlled rectifier with a purely resistive load, right? So we are having the 6 thyristors T1, T2, T3, T4, T5 and T6, right? So now if you check this waveform, this is for diode rectifier. Okay, now can I say that the difference between the two circuits, diode rectifier and a thyristor rectifier, is here we're having a controlled switches, and in the previous case it was a uncontrolled switches. Okay, if I put alpha equal to 0 degree, if I put alpha equal to 0 degree, yes, for these thyristors, then can we get the output voltage waveform which is similar to that of the previous case? Yes. Are you getting the point? If I put alpha equal to 0 degree, okay, then we'll be getting the output voltage waveform similar to that of the previous case. Okay, next, here also at a time two thyristors will be in a conduction mode, so output voltage will be getting is equal to line voltage waveform only. Okay, so that's why here the supply voltage, we are having the supply voltage waveform is nothing but the 6 line voltages. We are having the 6 line voltages. Okay, so which are those 6 line voltages? Just now we discussed. Here we are having the line voltages like VAB, this is a VBC, this is a VCA, right? Next we are having opposite to that of the VAB is a VBA, opposite to that of the VBC we are having a VCB, and opposite to that of the VCA we are having the VAC. Okay, VAC. So these are the 6 line voltages. In that, VAB is equal to VML into sine of omega t. VML into sine of omega t. Okay, so VML is a peak value of a line voltage, peak value of line voltage. Okay, so you can check corresponding to this instant we are having the peak value of the line voltage. Okay, next the angles are, this is like your pi by 6, this angle is like a pi by 3, right? This angle is pi by 2. Next here we are having a 2 pi by 3, right? 5 pi by 6, here it is a 2 pi, right? That is a 6 pi by 6. Okay, 7 pi by 6, here it is a 8 pi by 6, 9 pi by 6, right? 10 pi by 6 here, and 11 pi by 6, and here it is a 2 pi. You can check pi by 6, pi by 3, this will be like your pi by 2. Okay, after pi by 2 plus 30, that is a 2 pi by 3. 2 pi by 3 plus 30 means this angle. Okay, so this angle plus 30 means here it is pi, not 2 pi, here it is a pi, right? Okay, next pi plus 30 means this angle here. This plus 30 means 8 pi by 6 plus 30 this angle. Okay, so it is like we're having a 30 degree intervals, right? But I have written some of the angles. I have written some of the angles. Now, yes, in this circuit, we are having the two modes of operations. One is, yes, for alpha less than 60 degree, and second one is for alpha greater than 60 degree. Okay, we'll discuss alpha less than 60 and alpha greater than 60 degree. Okay, so first of all, let us identify alpha equal to 0 degree points for the respective thyristors. Okay, in the morning session, whatever we did for 3-phase half wave control rectifier, now first thing is we identified the alpha is equal to 0 degree points. Okay, for respective thyristors now. So similarly here we are having a 6 thyristors. So for 6 thyristors, we need to write the alpha equal to 0 degree points. So here you can check in this case, that is in the diode case, if you check in the diode and thyristor, what we have changed, we have replaced diode D1 with thyristor T1, we have replaced diode D6 with thyristor T6, like this. Okay, so you can check from this point to this point. Okay, from this point to this point, we are having a diode D1 is in a conduction mode. Before this instant, whether diode D1 is there in a conduction mode, diode D1 is not there in a conduction mode, because before this instant it is like a diode D1 was in a reverse bias mode. Okay, so means at this instant it is like our diode D1, okay, will be switching into the forward bias mode. Okay, so can I say that corresponding to this instant is nothing but this will be like alpha equal to 0 for thyristor T1. I am replacing now diode with a thyristor. I am replacing diode with a thyristor. You can check before this instant I am saying diode D1 was not there in a conduction mode, because in the continuous cycle, here VCB is the peak value, na? VCB is at its peak value. So if VCB is at its peak value, means which diode should be in a conduction mode? D5, D6 will be in a forward bias mode, whereas D1 will be in a reverse bias mode. So D1 will be switching into the positive values or will be forward bias mode only after this instant, only after this instant. So can I say that this point is like your alpha equal to 0 for thyristor T1? So I'm writing here, this point is nothing but alpha equal to 0 for thyristor T1. Okay, alpha equal to 0 for thyristor T1. Let me write here. This point indicates your alpha equal to 0 for thyristor T1. Okay, alpha equal to 0 for thyristor T1. Please check how I have identified alpha equal to 0 for thyristor T1. So for that, suppose if diode is instead of thyristor, if the diode is present, then actually in the case of diode, the thing is as soon as it becomes forward bias, it starts conduction. Na? Okay. So for that we have considered this waveform, and here you can check here diode D1 starts conduction from this instant. Okay. So like this means the meaning is from this instant it is a diode D1 is in a forward bias mode. Okay, so as diode D1 is in a forward bias mode, so definitely our thyristor also will be in a forward bias mode only after this instant. So this point is like alpha equal to 0 degree for thyristor T1, alpha equal to 0 degree for thyristor T1. Okay, in the continuous cycle you will understand why it is alpha equal to 0 degree. Okay, so next similarly you can check in the case of diode also. In the case of diode also, yes, do you want to say something? Okay, so similarly you can check for diode D2. Diode D2 is present here. Here diode D2 is not present now. Means can I say that at this instant or after this instant your diode D2 will be in a forward bias mode, and this instant is like your 2 pi by 3 na? This instant is like 2 pi by 3. So can I say that for the thyristor also, this instant, that is a 2 pi by 3, is nothing but alpha equal to 0. Alpha equal to 0 for thyristor T2. Now I am saying for thyristor T2. Okay. Similarly, you can check for diode D3 now. Diode D3 is not present here, but whereas it is present here. Okay. So it is like diode D3 is in a forward bias mode only after this instant. So can I say that this instant, that is the omega t is equal to pi, it indicates alpha equal to 0 for your thyristor T3. Alpha equal to 0 for thyristor T3. So you can check after 60 degree we are having alpha 0 for T1. Next after 60 degree alpha 0 for T2. After 60 degree alpha 0 for T3. Similarly, you can check this point will be definitely alpha equal to 0 for thyristor T4. This point will be alpha equal to 0 for thyristor T5. And again you can check after 60 degree means this point, and this point is like your 2 pi radian. 2 pi is nothing but again 0 degree. So can I say that this point is nothing but this point only? Okay, let me write here. So this point will be like your alpha equal to 0 degree right. So this is alpha equal to 0 degree for thyristor T6. So please try to understand. I am writing it as a alpha equal to 0, but omega t's are different. Omega t are different. Okay. So can I say that alpha 0 for T6 means omega t 0. Alpha 0 for T1 means omega t is equal to pi by 3. Yes or no? Alpha equal to 0 for T2 means omega t is 2 pi by 3. Alpha equal to 0 for T3 means omega t is pi. Alpha is equal to 0 for T4 means omega t is 8 pi by 6. Right? Alpha equal to 0 for T5 means omega t is 10 pi by 6. And similarly, alpha equal to 0 for T6 means it is a 2 pi, that is nothing but your 0. That is omega t is 0. Right? So these are alpha equal to 0 instants. The meaning is in the continuous cycle, if we apply the gate signal to the thyristor T1 before pi by 3, our thyristor T1 will not turn on at all. I am saying in continuous cycle, please try to understand this wording, right? Means when a continuous cycle is there, and if we apply the gate signal to thyristor T1 before pi by 3, our thyristor T1 will not turn on. The meaning is thyristor T1 will be in a forward bias mode only after pi by 3, right? So that indicates your alpha equal to 0. And how we have calculated these instants, how we have found these instants with the help of your diode circuits? Yes or no? right? So now because the diode is having a tendency that as soon as it becomes forward bias, it will turn on, right? So now, yes, now let us discuss the circuit operation. Okay, circuit operation. So before that, let me write alpha equal to 0 instants. Yes. So here for thyristor T6, let me write first T1. For thyristor T1, alpha equal to 0 degree means omega t is how much? Omega t is pi by 3. For thyristor T2, alpha equal to 0 degree means omega t is equal to 2 pi by 3. For thyristor T3, alpha equal to 0 degree means omega t is equal to pi. Similarly, for T4, alpha equal to 0 degree means omega t is equal to 4 pi by 3. That is 8 pi by 6, right? 8 pi by 6 means 4 pi by 3. For T5, alpha equal to 0 degree means omega t is equal to 5 pi by 3. That is a 10 pi by 6. And for T6, alpha equal to 0 degree means omega t is equal to 2 pi, or it is a 0 degree, right? Let me write 2 pi or 0 degree. Okay, 2 pi or 0 degree. Now let us discuss the circuit operation. Okay, for alpha less than 60 degree. Okay, for alpha less than 60 degree. So let me write for alpha less than 60 degree. Yes, I'm writing here. Okay, or let me write here for alpha less than 60 degree. Okay, what will happen? Now suppose alpha less than 60 degree means, suppose I am applying the gate pulse, okay, or I am keeping alpha is equal to 30 degree, right? We are having the conduction or the boundary between the continuous discontinuous conduction, that is at alpha equal to 60 degree. So we'll discuss what will happen at 60 degree, what will happen at less than 60 degree, what will happen at greater than 60 degree. Those things we are going to discuss. Okay. So now alpha less than 60 degree means, suppose alpha is equal to 30 degree. 30 degrees less than 60 degree, na, right? So alpha is equal to 30 degree means at which instant we are supposed to apply the gate pulse to thyristor T6? Come on. Alpha equal to 30 degree means at which instant, that is at which omega t we are supposed to apply the gate pulse to thyristor T6? For thyristor T6, alpha 0 means 0 degree, na? So if I want to apply gate pulse at 30 degree, means omega t should be equal to 30 degree, na? Alpha 30 degree means for thyristor T6, omega t also equal to 30 degree. Yes or no? Right? So let us consider, yes. How the 90 degree? Some are saying 90 degree. Okay. Most of them. Yes. For T6, I am saying, not for T1. I have asked the question for T6. Okay. So you can check alpha. Let us consider 30 degree. Let me write alpha equal to 30 degree, because definitely it is less than 60 degree. Okay. So this point omega t is 0 degree means alpha equal to 0 for T6. So 30 degree means we are supposed to apply the gate pulse to thyristor T6 at this instant, na? Right? Means at this instant T6 is fired. Similarly, where at which omega t we are required to apply the gate pulse to thyristor T1? For thyristor T1, alpha 0 means omega t pi by 3, right? So in that, add 30 degree means that will be your 90 degree, na? So this point will be your, at this instant we are required to apply the gate pulse to thyristor T1. Okay. Now alpha 30 degree means at which instant we are supposed to apply the gate pulse to thyristor T2? It is 2 pi by 3 means alpha 0. If alpha is 30 degree means it is a 2 pi by 3 plus 30. Okay. So 2 pi by 3 plus 30 means it is like your 150 degree, na? So this instant here, at this instant we are required to apply the gate pulse to thyristor T3. Similarly, alpha 0 for T3 means omega t is pi. Okay. So pi plus 30 degree. So that's why we are required to apply the gate pulse to thyristor T3 here. T6, T1, T2, T3. Next, definitely the T4 will come. Here T4. After that the T5. Right? And in the continuous cycle, the T6. In the continuous cycle, that is the T6. Okay. So what it indicates, at this instant we are required to apply the get pulse to thyristor T6, here T1, here T2, here T3, here T4, and here T5, right? Like this. Now let us discuss the waveforms and how the circuit operates. Okay, so now please check here. At omega t is equal to pi by 2, na? This is pi by 3 plus 30 degree means pi by 2. Okay, at pi by 2 means at this instant we are applying the get pulse to thyristor T1, right? So before T1, which thyristor pair will be in on state? If you check before T1, which thyristor pair will be in on state? Yes, it will be like, you can check, once T1 is turned on, at that time or before T1, which thyristor pair will be in on state? It is like a T5, T6. Please check up for the continuous conduction. Check for the continuous conduction. Okay, because before T1 we applied the get pulse to T6 na. So